Hello and welcome to the third installment of FTCOE's 5-part Society of Forensic Anthropology webinar collaboration series. For today's webinar, we have Dr. Sarah Getz presenting Transition Analysis 3 Age at Death Estimation, Past, Present, and Future. The Q&A session will be moderated by Michaela Askeles, a forensic scientist at RTI International. Without further delay, here is Dr. Getz.
Hello, and welcome to this webinar on the past, present, and future of the TA3 Adult Age of Death Estimation Method. My name is Dr. Sarah Getz, and I'm an assistant professor and program coordinator for the Forensic Investigation Program at the University of Wisconsin-Platteville. I'll be starting a position as a forensic anthropologist for the Oklahoma Office of the Chief Medical Examiner in January, so at the end of this presentation, I've provided you with my personal email and website so that it could be easy to get in touch if you have questions, regardless of when you're watching this video. In this presentation, I'll first provide a brief history of the TA3 project from its beginnings in the late 1990s through to its funding by the National Institute of Justice in 2014. I'll then describe the iterative process used to identify traits and develop their definitions. After that, we'll go through the general groups of traits within the manual and discuss the generic data collection form and the trait scoring manual that are available to allow you to score the features. Once you have a basic understanding of the traits and how to score them, I'll talk about the TA3 reference dataset collected as part of the NIJ project and how these data can be used to estimate age using trait data collected from an unknown skeleton. Finally, I'll provide a summary of ongoing work by members of the research team, planned work for the coming years, and areas where I think additional effort is needed. To understand the development of the TA3 method, it's necessary to give a brief history of the early work that shaped the direction of the project. In the early 1990s, George Milner and Jesper Voldsen were working on anthropological questions related to health and mortality in the past. They realized that to address their questions, more accurate and precise estimates than could be produced using existing techniques were needed. When they began working on their new method in 1996, the prevailing belief was that errors in age estimates were the result of poor statistical methods and not the skeletal traits used. So their research focused on the cranial sutures, pubic symphyses, and iliac auricular surfaces, which anthropologists were already familiar with. These features were separated into components and integrated into a new statistical framework that they called transition analysis. Importantly, during the course of this project, Milner and Voldsen began to realize that they could also look at other features throughout the skeleton when generating an initial impression about age. During their data collection and in the years that followed, they generated a list of features that would become the foundation of many of the TA3 traits that we'll discuss today. Since its publication in 2002, transition analysis has been tested in several published studies and adopted for use in both forensic and archaeological contexts. Using a free computer program, individualized maximum likelihood age estimates with associated confidence intervals can be produced for adults using whatever traits are available from the 33 possible scores. In this slide, you can see the maximum likelihood age estimates produced for a sample of skeletons from the Bass and Mercyhurst donated skeletal collections. Because Milner both developed the definitions for the original transition analysis components and collected the test data, this validation study can be considered a best-case scenario for this method. The line on the slide indicates where the estimates would fall if the method worked perfectly. In other words, if TA perfectly estimated the reported age for each individual, all of the dots would line up along the line. Individuals falling above the line were overestimated, while those who fall under the line were underestimated. As you can see in the green box, age can be estimated for individuals under the age of 50 with a relatively high degree of accuracy. Over the age of 50, age estimates can still be produced with relatively high accuracy and less bias than with commonly used phase-based methods, but underestimation of age becomes increasingly problematic. In their validation study, Milner and Voldsen attribute this increasing underestimation to failure of the skeletal traits to change with age in a predictable way after around age 50. In other words, age estimates become worse in middle and old age because we don't have adequate data in those parts of the lifespan. Although this idea had been discussed by other researchers, the authors provided a novel way to visualize these patterns. The graphs on this slide show individuals from their sample arranged in order of their known ages, shown as black dots, increasing from left to right. Gray vertical lines represent the estimated interval, and horizontal dashes indicate the maximum likelihood estimate. In a nutshell, the shorter the vertical lines, and the more closely they increase with increased documented age, the better the feature is for age estimation. As you can see in the highlighted areas, their results supported what we knew or at least suspected from other research. The pubic symphysis and auricular surface showed little regular change after the age of 50. The data for the cranial sutures were also presented in their paper, but showed even less useful age-related information. So although the original transition analysis method accomplished its goal of producing more accurate point estimates for adult skeletons, even using partial data, the method is hindered by its reliance on the cranial sutures and pelvic joints. In addition to failing to provide adequate information in a substantial portion of the lifespan, the cranial sutures may actually be reducing accuracy, and the pelvic indicators are frequently damaged. Additionally, even when all the traits are present, the method still produces estimates with wide intervals and increasingly underestimates the age of middle and older adults. It's at this point where Milner and Boltzann's original idea that other features may be contributing to age estimates provides us with a possible path forward. As part of the data collection for Milner's 2012 validation study of transition analysis, he generated a subjective, experience-based estimate of the age for each individual as he unpacked the box, but before he closely evaluated any age indicators. Contrary to what was expected, the experience-based estimates shown on the right graph cluster more tightly around the identity line and do not exhibit the same age-related bias in the estimates generated using transition analysis, which are shown on the left. While subjective experience-based estimation cannot easily be taught and is not an appropriate method for forensic or archaeological applications, it does support the hypothesis that there are more features in the skeleton than what have been traditionally investigated, which can be used to improve age estimates, particularly in middle and old age. Although I had worked with Milner as an undergraduate student in his bioarc lab and had completed my honors thesis collecting data from his list of low information traits using the Terry collection, it was not until I returned to Penn State to start my doctoral work in 2011 when I truly entered this story. At this point, Milner was convinced that integrating new features into the transition analysis statistical framework was the way to improve precision and reduce or eliminate age estimation bias. So, beginning in 2012, I began collecting data on the original Milner and Boltzann's list of new traits to code and systematically evaluating and refining them. At this point, both Milner and I also began applying for grant funding. During this initial trait development and data collection process, Milner trained me to use his existing list of traits that he believed contained age information, and I also generated subjective experience-based age estimates anytime that I went to a documented skeletal collection. The left side of this slide shows the estimates produced using original transition analysis and experience by Milner, while those on the right side show my estimates on a different sample. The skeletal diagram on the right side of the slide shows the location of the traits that were being investigated during this time and that potentially contributed to the experience-based estimates. When you account for differences in sample size and age composition, the results using transition analysis are almost identical. While it's obvious that Milner's experience-based estimates are more accurate than mine, the results of experience with only 500 to 600 known age skeletons even more strongly supports the ability of these low information features to improve age estimates, if they can be defined and documented in a way that can be taught to others. The basis for evaluating and refining traits in this project was logistic regression, which in this context is often called a transition curve. On this graph, the symbols on the top and bottom represent a single individual. 0, the trait is absent, and 1, the trait is present. Logistic regression is used to fit an S-shape or sigmoid curve to these data that represent the probability of a trait being present in an individual of each age across the lifespan. In a visual way, the steeper the curve, the more informative the trait is. As we'll come back to later, combining these curves based on the traits observed in each skeleton is the core idea of the transition analysis approach. In 2012, beginning with a list of 50 traits identified by Milner and colleagues, I began the iterative process of data collection, analysis, and refinement using the simplified process shown on this slide. First, we would identify traits based on experience or things in the literature, separate the traits in definable categories, and generate definitions for each of the variants. Then I would go to a collection. At first, I used the Bass collection, which was the largest and closest documented collection to me, using both sexes with individuals starting at 15 and ranging to the maximum age in the collection. Then, once the data were collected on paper forms, I would return home, enter them into an Excel file, convert all of the scores into binary comparisons. So many of the features had 3 to 8 variants, but we would reduce them down into binary comparisons to try to identify which of the features were relevant and which of them were not, and then evaluate the traits based on both the age distribution of the absent and present individuals, and then also the transition curves. So up on the top of the slide, you can see the good pattern, or a very strong age-related pattern, a steep transition with a clear distinction between those who did not have the trait and those that did have the trait. There's always going to be some overlap, but it was a very obvious pattern. It's also possible that the trait looked potentially bad, where the curve was present. You could definitely see an increase in age over time. But if we got additional individuals, it's possible that those who are present at the top of the graph would fill in, and then we would completely lose the age-related pattern. So if I had a sort of potentially bad transition curve, we would generate a minor definition change. We would add or eliminate categories. If it went through several more rounds of data collection like that, we would then ultimately eliminate that trait. And if the pattern was just terrible, I have it listed here as ugly, there was no apparent age information, it's entirely possible that either we misrepresented the definition and didn't capture what it was that we were actually looking for, or it's potentially that that trait actually has no age-related information and we just thought that it might. So we would create major definition changes, add or eliminate categories, and then again, after several rounds of testing, eliminate the trait. Here you can see the sample sizes for the 5 rounds of preliminary trait refinement I conducted at the BAS collection in 2012 and 2013, as well as the number of traits used, the number of binary transitions tested, and the features added and eliminated after each round. Once I identified a set of features that worked reasonably well, I then collected data on this group of features at 4 collections in the US and Canada in 2014 and conducted one more cycle of analysis and trait evaluation to select the 45 features that I used for my dissertation and with which we started the NIJ project. By 2014, we had a core set of features that provided age-related information for most of adulthood. It was at this time that both my dissertation and the much larger NIJ project were simultaneously funded. The goal of both projects was to expand the existing transition analysis framework to include traits from throughout the skeleton that provide information throughout adulthood. However, each project focused on a different application of this information. While the NIJ project worked with samples of modern people from multiple continents to generate a TA3 method for forensic use, I evaluated the traits in a single broadly defined ancestry group as a large-scale proof of concept of the approach for archaeological applications. For the rest of this presentation, I'll focus only on the NIJ project, but I'm also happy to answer questions about the results of my study. In addition to my previous work with Milner, testing, identifying, and refining traits, my roles in the new NIJ project, both as a graduate researcher and then as a postdoc, were to assist with organizing research trips, selecting samples from collections, creating the data collection forms and trait manual, taking trait photographs, entering our paper data forms into an electronic format, and conducting preliminary data analyses. The NIJ grant funded an international research team from the US and Denmark to identify and characterize new age-informative traits that could be used to improve our ability to estimate age throughout adulthood, characterize these traits in samples from around the world, and generate a new software program to produce age estimates. George Milner was the project PI, with Jesper Bolton and Steve Owsley as co-PIs, to work on the bones, the math, and the software components of this project simultaneously. Svenja Weisse, Peter Tarp, and myself were also hired as part of the team. As I just mentioned, a primary goal of the project was to identify and define a set of traits throughout the skeleton that provided useful age information. Ideally, we wanted the scoring areas to be easy to locate, even in fragmented remains. We wanted the trait definitions to be unambiguous and able to be learned by anyone just reading the manual for the first time. We wanted the traits to be distributed in as many parts of the skeleton as possible, and we wanted trait age at transitions to be distributed throughout all of adulthood to provide information in young, middle, and old age. So during our first data collection trip, Milner and I went through the traits and trait refinements we had generated during the previous 2 years and had several workshops and discussions with the other participants. We discussed the definitions, Bickered, I mean critically discussed the terms, made changes, created diagrams, and began adding photos to the trait manual to provide exemplars and clarify points of confusion. Throughout the team's multiple rounds of data collection, this process of discussion and the suggestion of new traits continued. By the time the team reached the third collection, the data collection form and trait definitions were essentially set. The team ultimately visited 4 different skeletal collections, with the first 2 being visited a second time to collect traits that had been added or modified to produce as complete a data set as possible. On this slide, you can see a generic version of the TA3 data collection form that's available for use with the current version of the trait manual. While this form does contain all of the data that you would want to collect from an unknown skeleton, it also contains some oddities that we use during our reference data collection that you may not want to collect for your particular case. For example, on the top of the first page, we have an area where each observer was asked to enter in their subjective experience-based estimate of age and sex. This was used to track improvements of relatively inexperienced observers estimating age just based on experience over time, but was also used to catch obvious errors in collection documentation that would trigger us to look closer at the collection information for that individual. On the back of the form in the bottom right-hand corner, there's also a block to enter in the documented information for each individual from the collection, which was unknown at the time of scoring, but that we would want to enter into our Excel file at the time I enter the data. Next to that is an area where I could initial when I had checked the form to make sure that all the fields had been completed, and an area to indicate that the form had been scanned so that if our forms were lost in transit, we would still have an electronic copy. There were also fields for the date when the form was entered into the computer and when the data had been checked. When the final version of the TA3 software is released, hopefully sometime in 2023, which I'll talk about a little bit later, a new version of the scoring form and trait manual will also be released at that time. Although there are nearly 80 distinct traits on the TA3 scoring form, I think that they can be made much more manageable by thinking about the traits in terms of 3 categories based on how they're scored, and then in different feature types, which I'll talk about on the next slide. The first category of features are descriptive. These are scored as either present or absent based on a description. They're usually a shape, which is difficult to categorize metrically, so these include things like depressions of the parietal bone, or curvature of the anterior margin of the first sacral segment. The second category of traits is features with non-metric thresholds. This includes numbers of a feature or a fraction or a percentage of a defined area. These are traits like macropores or bumps, and you will look at either there being a certain number of pores or a certain percentage of the area being covered with additional bone growth. Finally, the last category of features are those with metric thresholds. These can take the form of either a single measurement, 2 measurements such as a length or a width, or a defined area, a triangle or a rectangle with certain dimensions. These are particularly used in cases of epiphyseal fusion or the growth of spines, spurs, or projections, usually at tendinous insertion sites. In addition to these 3 broad categories based on how traits are scored, you can also break the traits down into a number of different feature types that are approached in a similar way. So once you learn how to score one, you can score all of the other features of that type regardless of where they are found in the skeleton. There are some exceptions and some caveats, so I do recommend that you read the trait manual closely, but once you have the basics, it will greatly simplify your data collection process. In general, I like to break down the TA3 traits into the following types: epiphyseal fusion or developmental traits, shape, lipping, bumps or bone deposition on surfaces, spurs, spines, or crests, macropores, weights and measurements, and then familiar traits of the pubic symphysis or the auricular surface that are often a part of other standard methods that you may be familiar with. It's at this point, before I go into talking about the traits a little bit more, that I'd like to make a disclaimer about the terminology used by the research team in the TA3 trait manual. Although some of the traits use standard definitions, such as remnant lines for epiphyseal fusion or lipping on the anterior margins of the vertebrae, we generally avoid the technical description or classification of features. Rather, the goal was to be as descriptive as possible. Many features that we scored do not have standard terms, or the terms may mean different things to different individuals. The goal of the team was to produce definitions that would result in individuals scoring exactly what was seen without worrying about classifying what the feature was or what caused it. The use of this generic terminology also allows easier entry for individuals just learning the method and for flexibility with translations as needed. With that out of the way, let's take a closer look at some of the feature categories I just talked about, starting with epiphyseal fusion. This is scored as not fused, partially fused, remnant line, or fully fused in the superior and inferior surfaces of L1 and L5, the iliac crest, and the medial clavicle. For each of these features, the definition of what constitutes partially fused or remnant line is the same, mostly based on the fact that in partially fusing bones, you can see a space between the bone and the epiphysis, whereas in remnant lines, the bottom of the joint between the bone and the epiphysis is filled in and looks as though it's scratched in the surface. Importantly, each of these bones has its own scoring area. For example, on the iliac crest, we're only looking at the anterior portion in front of the iliac tubercle. And for each of them, they have a different threshold for when a remnant line can be considered present. In the vertebra, it's a remnant line of any length. In the iliac crest, it's 10 millimeters. In the clavicle, it's 5 millimeters. So it's very important for all of these features, not just epiphyseal fusion, to look at the scoring manual, consider the diagrams, locate the scoring area, and be sure that you're using the correct thresholds to classify traits. In addition to the epiphyseal sites I just mentioned, there are several other developmental features that contribute to estimates of teenagers and young adults. These include fusion of the first and second sacral segments, the fusion of the spheno-occipital synchondrosis on the external surface, and the formation of the ventral rampart. The next major feature category that we'll talk about is shape, which does not have a metric threshold, but uses the description of the slope or overall shape of a bone to describe whether a feature is present or absent. For example, parietal depression is scored in the parietal bones, with A and B representing round or flat or sloped parietal bones being absent, and depressions on one or both sides being considered present. On the left side of the slide, you can see an example of shape for the humerus lesser tubercle. In young individuals, the anterior and lateral surfaces are rounded and curved, with a smooth connection between them. As age increases, the margin between the anterior and lateral surfaces becomes angled, but not elevated or lipped. As age progresses, an elevation occurs, which is later covered with roughening or lipping, which is not shown here. A similar process occurs in the L1 spinous process, which is shown on the right side of the slide, going from rounded to flattened, with later ossification of the ligaments and lipping occurring. On this slide, you can see some more examples of shape-related changes in the TA3 traits. Going clockwise, starting on the left, you can see the rounded and sharp margins of the first sacral segment, ossification of the sternal rib ends going from regular to irregular, extreme thinning of the rib body resulting in a rib shape called shingle ribs, and as an extreme change in angle between the second and fourth sacral segment, resulting in a feature called the sacral elbow. The next category is lipping, which is broadly defined as the addition of irregular bone growth around a joint surface. As with the other traits that I've mentioned, each one of these has caveats and exceptions and looks significantly different from one joint to the other, so it's prudent to consult the definitions and the photos found in the TA3 trait manual. On this slide, you can see examples of lipping around the C1 dens facet, trapezium, femoral fovea, medial epicondyle of the humerus, occipital condyle, and glenoid fossa of the scapula. The next general feature category are macropores, or pores penetrating the cortical surface into the trabecular bone that are greater than 1 millimeter in diameter. These are scored on the medial clavicle, lateral clavicle, greater tubercle of the humerus, and the inferior portion of the iliac auricular surface. One thing to keep in mind when scoring macropores is the possibility of the presence of subchondral defects. To distinguish between a subchondral defect and a macropore, look at the defect closely. If it has rounded walls with smooth edges and a filled-in bottom that does not expose the trabecular bone underneath, then it is likely you're dealing with a subchondral defect rather than a true macropore. The next general feature type is that of bumps or the deposition of bone on a surface, which is a little less intuitive than some of the ones that we've talked about so far. In this case, what we're looking for is an irregular deposition of bone on top of a surface. Although I showed you earlier that, for example, the edge of the lesser tubercle may change over time, you can think of that as a change in the topography of the bone itself without the addition of bone onto the surface. So here we're really looking for irregular ossifications that look like they could be scraped or pulled off of the surface, although we know in reality that's not really what's happening. Going back to our categories of features, these bumps are either scored as features with non-metric thresholds, such as a percentage of an area, like 1/3 or more of the anterior surface of the lesser tubercle of the humerus, or features with metric thresholds, usually a single measurement, such as more than 5 millimeters of bone deposition on the femoral head. On this slide, you can see examples of bone deposition on the medial clavicle, the anterior surface of the lesser tubercle of the humerus, the medial epicondyle of the humerus, the ischial tuberosity, and the femoral head. Continuing on this slide, you can see additional examples of bone deposition on the posterior sternal body, the anterior inferior iliac spine, the greater trochanter of the femur, and the posterior surface of the acetabulum. With the exception of some likely familiar features of the pubic symphysis and iliac auricular surface, as well as the weights and measurements included in the TA3 manual, we've reached the last category of features that I'd like to talk to you about, broadly called spurs, spines, and crests. These features are ossifications, usually at tendinous insertion sites, that are scored as either a length or a combination of a length and a width. On this slide, you can see ossifications of the olecranon process, the radial tuberosity, and the trochanteric fossa. Finally, we've reached the relatively familiar categories of the pubic symphysis and the iliac auricular surface. Importantly, if you're familiar with the existing transition analysis method, although the feature names are the same, there are a reduced number of categories, and the definitions and the thresholds for entering and exiting a category have changed. So be sure to read the definitions in the manual closely and take a look at the included images. In the new TA3 traits, we've included only the pubic symphysis and auricular surface categories and features that provide the best information compared to the other traits throughout the skeleton. So in the pubic symphysis, we score the surface morphology, presence of the superior protuberance, the ventral and dorsal margins, and the presence or absence of a symphysial collar, which involves the ossification of ligaments on the anterior surface built up to the level of the pubic symphysial face. As with the pubic symphysis, the traits scored for the iliac auricular surface are not scored in the same way as the existing transition analysis method. So again, be sure to read the definitions and the categories very closely. All three regions of the retroauricular area, the superior exostoses, inferior exostoses, and posterior area, are still scored, but in different categories with different definitions. The inferior joint porosity is also still scored, while all other traits have been eliminated. With that, we've now reached the very last set of features in the TA3 trait manual, which I generally call weights and measures. These involve a maximum length or height measurement for the humerus, os coxa, tibia, and calcaneus, as well as a measurement of the bone's weight in grams. These data were originally collected as a way to standardize our subjective classification of bone weight as normal, light, or feather light. At this time, these weights and measures are not currently incorporated into any of the transition analysis methods of estimating age, but we hope to use them in the future, potentially as a replacement for those subjective classifications. To wrap up this introduction to the TA3 traits, I'd like to leave you with some advice and some words of caution. The trait thresholds listed for each feature in the manual, such as length of lipping or the number of macropores, were selected to maximize the age information provided while minimizing the time needed to make a decision. In many cases, the thresholds represent a size or extent of a feature that's clear and distinct. Once you become familiar with the traits, a glance at a bone should be enough to determine whether a trait is present. Whether you're just learning the traits or have scored them in thousands of individuals, consult the manual often and measure frequently. Many of the features, particularly those that occur only in very old age, appear only rarely, so don't be concerned if you don't see them in your casework or test samples. Don't be tempted to allow your thresholds to creep downwards until you classify the slightest hint of a trait as present. On this slide, you can see some examples of the olecranon process of the ulna, the iliac crest, lateral clavicle, and radial tuberosity that do not meet the threshold requirements for the trait to be present, but might tempt some individuals who are caught without a ruler.
Now that I've introduced the concept of TA3 and the traits, we can now talk about the NIJ reference data and how that information can be combined to produce age estimates. As I mentioned previously, the team collected reference data from 4 collections, which resulted in a sample of nearly 1,700 modern, documented individuals, each scored for the 80 age-informative traits in the scoring manual. The skeletal samples evaluated by the team were selected to represent a cross-section of modern populations from the US, Europe, Africa, and Asia. All males and females older than 15 years of age with adequate documentation had the potential to be included in our sample. Skeletal samples from each collection were selected several weeks prior to data collection, and blind scoring lists were generated. In other words, the skeleton numbers to be evaluated were known, but their demographic information was not. Data were collected using versions of the trait manual and generic data form shown earlier in this presentation, and data were collected in teams of 2. One individual was the primary observer, while the other was the primary recorder, although consultation was allowed. Teams were rotated to prevent systemic bias or definition shifts over time. Cases of obvious commingling that could not be resolved or obviously erroneous documentation, such as an elderly female who was listed as a young adult male, were eliminated from the sample. Individual traits were not scored when there was obvious pathology beyond that which was related to the trait being scored, such as arthritis, or trauma to the area or directly articulating surface. Traits that may have been impacted by another injury, but that were not directly involved, were still scored. For example, a fracture of the tibia may have affected degeneration of the hip. However, we can't say for sure that that's true. Additionally, in a case where the entire skeleton is not recovered, we wanted to account for variation that could result from injuries in sites that we could not observe. The team was ultimately successful in identifying and characterizing features with median ages at transition in all portions of the adult lifespan, from the late teens through to middle age and into old age in the late 90s, and believes that this information will be the key to producing accurate and unbiased age estimates for middle and old age adults. This slide shows the information provided by the TA3 traits in a slightly different way. This figure was produced by Jacqueline Galamani, who is currently a doctoral student at the University of Nevada, Reno, using TA3 trait data that she collected from over 300 individuals at the Santiago Subactual Osteology Collection as part of her master's thesis. Here you can see the transition curves for all of the traits superimposed on a single graph. This clearly illustrates the density of information provided throughout adulthood. If you'd like to read more about the study and see the other graphs comparing the TA3 traits to the density of information available in the pubic symphysis, this paper is available in early view in forensic anthropology, and I can also provide a copy upon request. At this point, it's important to make a distinction between the TA3 traits and the methods used to translate the reference data into age estimates. While there's only a single set of TA3 trait definitions and scoring procedures that will not change moving forward, there can and are multiple different approaches for using reference data to estimate age for an unknown skeleton. In other words, at this point, there is no single TA3 method available and recommended for use. The options that have been and are currently under investigation include the TA3 beta software program introduced by Steve Owsley in 2018, a simplified transition analysis approach that I used in my dissertation and later in a 2021 test of the traits, and variations of the original transition analysis framework using the features by Milner and Boldson, which was the original plan for the NIJ grant. Let's first take a look at the TA3 beta software that was released by Steve Owsley for public testing. This is the approach that many of you maybe have heard about and some of you might be currently using. The initial version of the software was provided to participants at TA3 workshops at the American Academy of Forensic Sciences and American Association of Physical Anthropologists in 2018. Several versions with minor modifications were released for testing, with the last being updated in October of 2021. The program has two data entry modes. The first involves clicking through the submenus for each area of the body, which correspond to the sections of the data collection form, and selecting each feature score using images and the diagrams provided, which are those in the trait manual. The second mode is an electronic representation of the data collection form, which allows you to quickly click the buttons to enter your collected information. Regardless of which data entry mode you select, the program provides you with a summary of the data you've entered and uses the same set of R code to analyze your data. Despite its name, the TA3 beta program uses a black box machine learning approach rather than the transition analysis approach used in the original TA method. For each case, a random generalized linear model predictor is trained using a portion of the individuals in the TA3 reference sample and then applied to generate an age estimate for your unknown individual. The performance of the model in the training sample is visualized in a scatter plot, and the sample size, correlation coefficient, and standard error are provided, along with the predicted point age estimate and a 95% interval for your case analyzed. Despite anecdotal reports of the program's success for estimating age, the method had not undergone systematic testing using a large documented reference sample. So in 2021, Jacqueline Galimani and I tested the TA3 beta software using over 500 documented skeletons from Greece and Chile. Well, we presented our results on a poster at the 2022 AFS meeting and are in the process of writing up these data for publication. I'll present some key results here, but the poster is available for download from my personal website linked at the end of this presentation. To estimate age for each individual in our test sample, one of two methods was used. First, TA3 trait data were entered directly into the TA3 software. This allowed us to evaluate the interface and to generate estimates. Second, the TA3 analysis file, which is written in R, was modified by Jacqueline to allow for batch analysis and extraction of associated analytical data that's not currently provided to the user in the program's output. This loop file, which was used for analysis, is provided on GitHub with a link on the poster provided. A sample of individuals was analyzed using both approaches to ensure that the modified file was functioning as intended. This slide shows graphs similar to those presented earlier in this presentation, with the exception that inaccurately aged individuals, those where the documented age fell outside of the estimated interval, are shown in red. On the left are the results from the Athens collection, which are mostly complete individuals with the majority of the TA3 traits present. On the right are individuals from the Santiago subactual collection, which were more variable in their preservation. While the overall accuracy of the program in the combined sample was 84.5%, there were significant differences in performance between those under 40 years of age and older individuals, particularly when complete skeletons were used. Systematic age estimation bias was also a problem. Contrary to other approaches, overestimation was a problem at almost every age until you reached the upper decades of adulthood, about 70 or older. This problem was more pronounced in younger individuals and in those with complete sets of TA3 trait data. The precision of the estimates generated by the program were also an issue, with the intervals produced for complete individuals generally ranging between 30 and 40 years for most portions of the lifespan using all of the available features. When incomplete skeletons were used, the intervals were more variable in length, but because of the black box nature of the approach used, it's not possible to investigate this pattern in more detail. Finally, one additional issue we discovered in our evaluation of the TA3 beta program was a lack of transparency in the sample used to train the machine learning model. The implementation of the random GLM package used in the software only uses skeletons from the reference sample with all of the traits from your unknown skeleton available. As you might expect, this severely limits the sample size, particularly when complete skeletons are used. This pattern is shown on the graph on this slide. As the number of traits in the unknown individual increases, the sample size used to train the model drops dramatically. Importantly, there's no way to extract information about the age distribution or sample origin of the individuals selected for use from the reference sample from the existing method, which makes interpretation of these results and comparison with other samples problematic. So let's quickly summarize the results of our investigation into the TA3 beta program. Despite its name, the program does not use a transition analysis approach. Although the average sample accuracy was acceptable, looking at the sample by decade revealed that the average accuracy for individuals under the age of 40 was poor. Although the method performed reasonably well for individuals above the age of 40, the precision was still poor, with age interval lengths of 30 to 40 years for complete and nearly complete individuals. The program also uses a small fraction of the 1,700 individuals in the TA3 reference sample to generate age, and the composition of the sample cannot be determined. Importantly, this avenue had to be investigated in order to determine that it was not the best path forward. It's also important to keep in mind that even if the program had functioned as intended, it would be difficult or impossible in its current form to allow investigations of sample and population differences around the world, or to evaluate how the use of different numbers of features would impact the results. For all of these reasons, I do not recommend the use of the TA3 beta program for either forensic or archaeological applications in its current form. Although the machine learning approach did not produce results adequate for use in forensic or archaeological applications, there's still evidence that the TA3 traits can be used to produce useful age estimates. In 2021, at AFS, I presented a preliminary investigation of the TA3 traits used in a simplified transition analysis framework. This investigation used the TA3 reference dataset, but converted each of the non-binary trait variants into a dichotomous pair. The most age-informative transition, based on the appearance of the transition curves, was selected for inclusion in this analysis. For each trait, probabilities were generated from logistic models fitted to the data for the entire reference sample, and then these were combined into a single log likelihood function from which a maximum likelihood and 95% confidence interval were calculated for each individual. Here you can see the maximum likelihood point estimates produced using the existing transition analysis approach based on the cranial sutures, pubic symphyses, and iliac auricular surfaces on the right, as well as the simplified transition analysis approach described on the previous slide using the TA3 features. The line of perfect agreement between documented and known age and a regression fitted to the estimates are both shown. As you can see on the left, the original transition analysis approach showed age estimation bias in young and old age. However, as you can see on the right, the fitted regression is nearly indistinguishable from the identity line. In other words, by using traits that collectively provide information for all portions of the adult lifespan, we can resolve the issue of overestimating the age of young adults and underestimating the age of older adults that occurs in essentially all existing methods. This simplified approach also outperformed the machine learning model, which I also tested using the same sample. The simplified transition analysis approach also demonstrates a significant improvement in terms of precision. On this slide, the gray lines show the age interval estimated for each individual using both methods. While the overall percentage of individuals whose documented age fell within the estimated interval was essentially the same, the average length of the age interval produced using the new traits was reduced by nearly 50%, from 32.4 years using traditional skeletal features to 17.2 years using the new TA3 traits. This graph combines information about the relative trade-off of accuracy and precision in commonly used methods and the simplified TA approach I just described. Given how the TA3 trait data were combined in my study, the accuracy seen here for the TA3 trait should be viewed as a worst-case performance scenario using a transition analysis-based approach. While this test demonstrated that similar accuracy with greatly increased precision can be produced, there's still work to be done. George Milner, Jesper Boldsen, and a team of students have been working on a revised version of the transition analysis framework for several years. Issues that are currently being investigated include which traits should be used and whether more data produce better results. There's significant evidence from preliminary investigations, including my dissertation, that they don't. Whether to use the right or left sides of the body, or both, particularly when the scores are not the same. Whether sex and population-specific probabilities generated from reference data produce better results, or whether increased sample size is more important. How best to deal with correlated features, and whether a prior distribution, similar to the forensic or archaeological hazard models used in the existing transition analysis program, are needed. A new TA3 software program, an updated scoring manual and data collection form, as well as associated publications describing the traits and analytical procedure are planned for release in 2023. So with all of this in mind, in addition to a new software program and scoring materials, what does the future of TA3 look like? In my opinion, the future of the TA3 traits lies in the investigation of substantially larger samples than have been looked at so far. Given the extreme time and expense needed to travel to skeletal collections, as demonstrated by the NIJ project, these will either include collaborative databases, such as occurring for sex and ancestry investigations, or the use of computer vision and machine learning techniques to more effectively utilize large medical imaging databases. Larger samples will also allow for the use of new statistical and methodological approaches for generating age estimates and investigating the effect of sample size and missing data on our results. These will also allow for refinement of the current features and investigation of other traits that may have age-informative potential. Finally, interdisciplinary investigations are also needed to produce a better understanding of the biology of aging, the factors affecting variation among groups, and how, when, and why features are expressed in the skeleton. While the TA3 traits have demonstrated their age-informative potential, we've only just begun to scratch the surfaces of differences among populations, why these may exist, and how they would impact our adult age estimates. The multi-decade process of developing the TA3 traits would not have been possible without the small legion of collection managers, research assistants, and students who offered their time and resources to make this project possible. I'd also like to thank NSF and NRJ for funding portions of this research and to everyone who made data collection possible. I'd also like to take a minute to thank the Society of Forensic Anthropologists for inviting me to present this webinar and to the Forensic Technology Center of Excellence for coordinating and hosting it. Additional information about the research referenced in this presentation can be found on my website, where I also post updates about the latest TA3 related publications and events. Although I'm sometimes a little slow to respond, I'm also available via email for TA3 related questions and for inquiries about TA3 training workshops.
Hi everyone, I'm Michaela Askeles. I'm a forensic scientist from RTI International, and I'll be your moderator today. If you do have any questions, feel free to just put them in that Q&A pod there. But thank you so much for the informative presentation, Sarah. We'll go ahead and get started. So it looks like our first question is a little technical, but the person's asking if it's possible to view the code used to create the TA2 and TA3, if that's GitHub or .txt.
That's a great question. I guess to answer that, I first have to clarify the original transition analysis was the Bolton et al. 2002 method, which had the original software package. What people typically call TA2 is just a slight modification of that package by Steve Owsley. He changed the way the data are visualized in terms of bar graphs rather than curves, and also updated it to work with new versions of Windows. So TA and TA2 were not released, as far as I know, by either Jesper Bolton or Steve Owsley. So the code for those is not available. TA3 is available on GitHub if you search for it. And also the modified batch file that Jacqueline and I used for our 2021 evaluation is also available on GitHub, and there is a link on the poster posted on my website.
All right, perfect. Yeah, thank you for clarifying that for everyone. And it's great knowing that there's a distinction between those two. All right, the second question asks, have there been any studies or research looking into the etiologies of some of the traits used in TA3, like degenerative or osteoformative pathologies or activity markers, etc., and their association with age and sex?
So that's a great question. Other researchers have published papers on lots of the other traits, not necessarily in exactly the way that we've defined them, and looked at their associations with age and sex. For this project, we're primarily just looking for an age-related pattern, and then we're testing to see if there were differences between sexes, if the age-related pattern held across populations. So we looked at the samples from 4 different continents. And so at this point, we have a set of traits that we know provide age-related data. There's actually some of them that upon further testing, we realized that
might not work as well in all groups. So that's something that's still under development. But a lot more work is needed, especially across different disciplines, to figure out why these may differ across groups, and why they're being created in the first place. So the team has not really delved into that a lot, but there is information out there for a lot of them.
Okay, gotcha. Yeah, hopefully more research can be done in the future on that. All right. So it looks like the next one seems like one of the goals of the TA3 project is identifying traits throughout the skeleton. What is the distribution of new features in the skeleton?
So on that slide that I put up a couple of times, there was a diagram of different numbers of traits shown in different regions. And one thing that you might have noticed is that there was a really high density of traits that we looked at in the skull and the lower limb. And unfortunately, those are two areas where we ended up with very few traits overall. We tested dozens and dozens of different traits and different variants and different categories within them. And we just weren't able to find anything that provided as much information as everything else in the skeleton. So for future investigations, those are definitely areas where we would like to look for more. But other than that, they're distributed throughout the rest of the thorax, pelvis, upper limb.
Gotcha. Yeah, no, that makes sense. All right, and then in your investigation of the TA3 traits, you mentioned a simplified transition analysis approach. Can you kind of explain more about how this is different than what was used in the existing transition analysis software, for Boldson in 2022?
Yes. I'm glad that someone asked this question, because I really didn't think I had enough time to go into the details of that. And actually, that was one typo on my part. I was talking about the original Boldson 2002 method. And so how my simplified approach that I used in my dissertation and in my test of the traits differed in a couple of different ways. First, the original approach took a single joint like the pubic symphysis or the auricular surface, each of those features, and broke them down into many categories and looked at the transitions among all of those. So it was a multi-phase transitions that were incorporated into that program, whereas I separated all the traits into binary components. So that's the first one. I was only looking at one feature at a time. The second thing was that the original Boldson method included a correction for correlated traits, and he's published on that as well. So basically the idea is that if you have multiple independent features, and you assume that they're all telling you different information, that they're all independent, and you add them together, basically your age interval is going to be more narrow than it would be if they're all if those traits are actually correlated, if they're actually providing you information about the same underlying process, for example, your age interval is going to be way more narrow than it actually should be. Basically, we're going to say that we're way more confident than we could be otherwise. And so they implemented a mathematical correction for correlated features, and I did not do that, which means that in theory, my method should be working worse than that original one in some ways. The other thing is that I did not use any sort of prior distribution. So the Boldson method includes both a forensic and an archaeological prior. Basically, one is homicide deaths and one is natural mortality. So essentially what it does is say, if you're the oldest set of traits, like if all of your traits are in the oldest phase, we know that there's a probability that you're going to be 70, that there's a probability that you're going to be 80, that you're going to be 90 or 100, but you're way less likely to be 110 than you are to be 80, even if you have the oldest versions of the traits, because we just know that there are fewer 110-year-olds in the population. And so my simplified approach does not include that at all. So it basically just says you're equally likely to die between 15 and 110 and end up in a reference sample. So there's a bunch of like minor statistical things, but basically all of those things are meant to improve the results. So the fact that we're getting essentially the same accuracy with greatly increased precision, even without all of those sort of bells and whistles to the method, means that there's a lot of age information in the traits that could potentially improve our estimates.
No, yeah, that's great. Yeah, I didn't even think about all those things you pointed out. So
Oh, sorry. One additional thing, really quick. In that investigation, I also took out any traits from the pubic symphysis and the auricular surface, so that those estimates were produced only using non-traditional indicators. And I do think the results could be improved by some of the features in those joints, but the goal of that original study was to kind of prove the strength of the traits without them.
Got it. All right. I think so basically, once you've collected all this TA3 data, what can you do with it at this point, or what can others do with it?
So unfortunately, at this point, I think there is a question a little bit later about reiterating why I think we shouldn't be using the TA3 beta software. But because I recommend not using that software, there isn't really a way to generate age from those trait data. I've gotten a number of inquiries from people asking if I still think that they should be collecting these data, even if they can't do anything with it at the moment. And I do highly recommend that you should, because I do think that we're going to be able to produce estimates with them coming up. So especially if you will not have access to your skeletal collections or to your cases a year or 2 years from now, I highly recommend that you still fill out the form and take the photos so that you can use the methods downstream.
Perfect. Yeah. And I don't know, do you have an estimate on, in the future when all of that will be up and coming?
So I just spoke with Jesper Voltsen and George Milner, or I spoke to George Milner, and he gave me an update on what Jesper is up to. And their plan is to have this out by the end of 2023. Whether that will actually happen, I'm not sure, but that is the goal, to have it sort of submitted and also have several research articles describing the traits and the method behind the software, as well as an updated software package by like mid to late 2023.
Oh, that's great to know. Yeah. And we understand, there's always delays and everything, but that's great knowing that, around 2023. All right, we have a longer question here. I'll go ahead and just repeat it. The audience member says, "Hi, I'm working on an honors thesis at the University of Texas at Austin, and I'm assessing the applicability of the TA3 to archaeological indigenous populations. I know that the manual stresses eliminating bias through blind recording by not considering any cultural and environmental information. With what we know today about certain external stressors affecting the skeletal system, why is cultural context not considered by TA3, especially for populations who experience high levels of violence and stress from the effects of colonization?"
That's an excellent question. And I think I can answer that in kind of two ways. The first of which is the initial TA3 program developed by the NIJ grant was only focused on modern people. And so the idea was to try to develop a method that could be applied to any forensic case, regardless of population. Obviously, we only started with 4 collections, and there is actually some evidence that we might not be able to have a universal method. I'm still of the opinion that it's possible. So we'll have to see what happens with that. In terms of applying the TA3 traits to archaeological or bioarchaeological investigations, I can speak a little bit to that because that was the focus of my dissertation. Once the NIJ project was funded for forensic work, I kind of shifted gears to look at the traits in a different way. So I started with modern collections, and then went back to pre-World War II collections with the individuals who primarily lived their lives in the late 1800s and prior to World War II. So in an area of, pre-antibiotic, pre-modern food, pre-US mobility, to get a better idea of whether the traits were functioning the same in those populations, and then went back to St. Bride's in London. So looking at a historic collection with people that, again, were living a different lifestyle than those in the United States, all within one broadly defined ancestry group, broadly sort of European derived populations, and then went back and looked at archaeological collections where I did not know the age and sex of the individuals, but from late medieval and early modern period Denmark, and looked at how modern commonly used methods were functioning. Were they giving us the same results compared to the transition analysis traits? And basically what I found is, regardless of differences within those populations in terms of health status and disease and trauma and arguably activity level and all sorts of things, we did not see dramatic differences in any of the traits that I looked at. And so it was evidence that we could take the traits, or at least the selection of traits scored the way that we defined them in modern people, and use them appropriately for archaeological use. That said, if there are joint surfaces that are particularly affected by a particular disease, so in one collection I looked at outside of that study, we had a lot of tuberculosis affecting L5. That's something that you have to identify and not score. And the other thing is that your particular population that you're looking at archaeologically might be arguably more variable than the sort of European-derived populations that I looked at in my study. So I can't guarantee you that they're going to be the same, but all available evidence we had is that these patterns are so broad and there's so much variation in age indicators and in the sample that we looked at that you should be getting adequate results regardless of the population you're applying it to.
Yeah, and for whoever asked that question, hopefully Dr. Getz answered everything for you, but feel free to reach out to her with anything further. Another question we have is, do you recommend scoring joint surfaces that have undergone a surgical replacement?
I do not. And I also don't recommend scoring the other side of those joint surfaces. Now, as I mentioned, if you have a joint surface, like let's say you have a knee replacement, and obviously you can imagine that then changes the biomechanical functioning of the hip. It would be up to you to take a look at that and really think whether it looks significantly different than the other side if they hadn't had a knee replacement on that side, and whether or not to score it. But generally speaking, we continued to score all of the joints that were not directly affected by a surgery or a trauma, specifically because if you had fragmented remains or you only recovered one bone, we wouldn't be able to see any of those joint replacements or traumas elsewhere in the skeleton. And then it also becomes sort of a thought exercise in terms of, okay, did that knee replacement affect functioning of the cervical vertebra, for example? It entirely might, but then we could potentially arguably say, let's not score anything. So we really didn't want to go down that rabbit hole. So don't score anything that's directly affected by a surgery or a trauma or a pathology, but then use your best judgment in terms of whether to include other things. Because arguably, a lot of the things that we're looking at are related to pathological conditions like osteoarthritis. So yeah, how affected those are is a judgment call.
Great. All right, and we have another question. Is there a scope in the future for examining individuals with congenital conditions using TA3?
I am not entirely sure exactly what that question is asking. So if they'd like to clarify, I'm happy to come back to it.
Yeah, if the audience member who asked that, if you could just clarify in the Q&A pod, and we'll come back to that question shortly. It seems that, I know we kind of touched on this already, but if you could just reiterate or maybe elaborate again on why TA3, the beta, should not be used for forensic casework.
Mm-hmm. So there's a couple different levels to why I think that it should not be used. One of the most important is that a large majority, obviously not all, but of forensic cases are going to fall in that under 50 category where we're getting extremely poor accuracy. So if you saw on that last summary slide that I presented, especially when you have complete or nearly complete skeletons, about 50% of the individuals are being inaccurately aged. And again, by inaccurately aged, I mean that their documented age was not falling into that 30 or 40-year interval, which means that the estimate is pretty far off. Even for those who are accurately aged, their documented age is falling into that large interval. We're getting overestimates of age for everyone, which means that there's something systematic going on behind the scenes that's creating a lot of inaccuracy in the program. And perhaps most importantly, well, I don't know, accuracy and precision are pretty important for forensic casework, but also important for forensic casework is that because there's a behind the scenes selection by the program that we cannot recover, regardless of whether you go into the code or not, we cannot figure out what individuals it's using to train that model. So that means we don't know the age distribution of the individuals in the reference sample that's being used. We also don't know which continent or which sample the populations came from. So it's entirely possible that on your forensic case, it only selected all the individuals that had the same traits, which maybe they're from Thailand or maybe they're from South Africa. And at this point, we don't really know enough about the population differences in our samples to be able to say how that might affect things. So you can't really even say the reference data that are being used, which is really problematic. And the other thing is that the reference samples are really small. So I think we're not taking advantage of the full information that's in those 1,700 individuals. So for all of those reasons, I would say this is not the approach to use. And Dr. Milner and Dr. Boldson have been working on that updated transition analysis approach, which was always sort of their plan from the beginning. But Dr. Owsley really wanted to try this new approach, which has been effective in other areas. So again, we really did have to try it to know that it wasn't going to work. And it might work in a different configuration. But with his recent passing, we're not really sure what's going to happen with that at this point.
Yeah, thank you for answering that. Let's see, we have another question. Why does TA3 exclude environmental and cultural information about the population?
So the goal of this, again, was really to create a method for forensic work. And because we are generally not able to accurately estimate population affinity or ancestry from our skeletons, or even if we can, that broad classification of population's affinity or ancestry doesn't really tell us anything about the specific group necessarily that individual came from. And so even if we could factor in environmental or cultural information, we wouldn't know that for our unknown skeleton. So we wanted to create a method that was generally and broadly applicable. And so the other thing with that is, I apologize, I lost my train of thought. We want it to be broadly and generally applicable. The other thing is that for most of our collections, we don't have that information. So although collections have gotten a lot better about collecting a lot of information about the people that are in them, we do not have the kind of data that would really allow us to enter that information into the program. So I really do think that we need these investigations about the impact of culture and environment and biology and genetic variation and all sorts of things on the formation of these traits. But we also need the development of the methods that are really practically applicable. So we really need the bones, and we need the biological investigation, and we need the statistical investigations all happening on different fronts. This is really just the beginning of this process. And really, you can kind of think of it as a large-scale proof of concept for moving the field in kind of a different direction.
Great. All right, I think we're, I see the audience member has clarified their question on congenital conditions. I'll go ahead and read aloud. They say, in my research, most traditional age estimation techniques aren't reliable for individuals with various congenital conditions due to either advanced or delayed skeletal and dental maturity in non-adults. Similarly, degenerative age changes in the skeleton, especially relating to pathological changes, happen at different ages to other individuals in their osteological cohorts. Just curious if the TA3 model could help pick apart some of these issues if it had a sufficient sample for the base data.
Ooh, not an easy question. I'm gonna go ahead and say I don't know. There's a lot of variation in the traits, even among the individuals we saw. And what we saw is that a lot of these features that we investigated had to be thrown out because maybe they're more related to activity or they're more related to some other factor that's not necessarily age that we couldn't pick up on our sample. So I actually don't know how a lot of these features would function in an individual. It might be also just what they were doing or moving. So for example, some of those proximal femoral traits, there's been some suggestions that the reason why our lateral trochanter features are working is just because the act of kind of stabilizing you, like if you're standing up for a certain number of years of not necessarily activity, but just being able to stand upright, we're getting a signature of age. So it might kind of depend on what sort of congenital conditions you're talking about. I would actually be really interested in talking to you one-on-one if you'd like to contact me, and we could talk about this in a little bit more detail. But the short answer is I don't know the answer, but it's really interesting.
Yeah, perfect. So yeah, if that audience member just wants to contact Dr. Getz afterward to talk more about this, that'd be great. All right, and I know you've already again defined TA2 and discussed that, but someone has been asking, understanding that you've worked primarily on TA3 and not TA2, and you don't recommend using the TA3 beta version, do you recommend using TA2 in forensic work?
That's a great question. And in terms of working on it, I began training in 2006 using the original TA2 or TA at the time, and then TA2 method that was available, and have been doing research since. I actually have a new paper coming out in the next couple of months looking at how to use the TA2 program effectively. So whether to use sex or ancestry specific selections within the program, what is the effect of the prior distributions, and looking a little bit more on how to use it effectively. I actually do recommend using it if you're going to be using the pubic symphysis and the iliac auricular surface, maybe not so much the cranial sutures, although I'm still investigating how those impact results. If you're going to be using those traditional features, I really do think that combining information from the different areas of the skeleton in a statistical way is the way to go. So I would advocate for using those data, and it would be something that I use regularly in my casework.
Okay, great. All right, and then we have another question on, is there a method you recommend using for archaeological populations?
I would still recommend using the TA2. You can use either the uniform or the archaeological prior distribution for that, looking at the pubic symphysis and the auricular surface. I will say that when the TA3 method does come out, I really recommend using that. If you're interested in my dissertation, I have some figures looking at our ability to evaluate age for archaeological samples, particularly those where the pelvic joints are damaged. And we can estimate significantly more of the sample, 30 to 40% more of the sample, using these traits throughout the skeleton than we can using traditional methods. But using anything that is phased-based will give you essentially the same pattern regardless of the population that you're looking at. So there's also some more information about that in my dissertation, or I'd be happy to talk to you about it. But really, anything that provides you an individualized age estimate would be the best for archaeological use.
Awesome. Now, I know you already mentioned, up and coming work. If you want to maybe elaborate on some of the things that are coming up, or
so at this point, I'm not really sure what else will be sort of coming down the pike. I'm continuing to work on evaluating the traits. I'm going to be publishing on those results, as I mentioned, from the TA3 validation study, just in case anyone wants to reference it or is not aware of the kind of patterns. Because again, the TA3 beta does work sort of anecdotally, especially if you have people in middle age or just looking at one case at a time. It's only when we look at really large samples that you start seeing these patterns. Hopefully in 2023, there's going to be the paper regarding the traits, and also the development of the new TA3 method based on the original transition analysis framework, and the new software. Oh, also, I'm currently working on updating the trait manual and the data collection form to make it more user-friendly with additional images and diagrams, and that'll be associated with the new software as well.
Yeah, that would be great to see new images and everything. All right, it looks like we have a couple more questions here. So we're talking about the future. Someone's asked, so do you think in the future AI will be doing the IDing by scan data, CT scan as Meyer, and more data is collected in modern forensics?
That is an excellent question. I absolutely think that CT, in my opinion, is the way forward. At this point, not all of the features within transition analysis can be evaluated in CT, but I have been working on a project, especially for use in medical examiner settings, to figure out which traits could be extracted from CT and how many of them would be enough to produce accurate age estimates. So in the future, as our ability in image processing to auto-recognize some of those features and automatically extract them, I think that will be the way of the future. I think we're still a little way off from there, and there's a number of steps before we get to that point. But yes, using medical imaging databases, especially CT, is going to be one of the only ways that we're going to get big enough samples to really refine this for the future and to get better controlled environmental and cultural information.
All right, thank you for answering that. I know that one was a little bit scrambled with the wording, but I think we got it.
Yeah.
All right, another question is, how would you handle fragmentary or partially complete skeletal remains? How fragmentary is too fragmentary to apply a TA method?
That's also a really good question. Part of it is we don't know. In the existing transition analysis with the skull and the pelvic joints, generally speaking, I like to have features from at least 2 of the areas. Generally, if you have at least a handful of features from the pubic symphysis or from the iliac auricular surface or retroauricular area, you're good to go. You can generate an estimate from one or the other, but generally it's recommended. The whole premise of the method is to combine information from different pieces. If you just have the skull, you're probably not going to get a very good estimate. You're probably not going to be wrong, but it's probably going to be about 80 years wide. So I don't really recommend that. So I generally like to have maybe at least half of the features, not necessarily from both. In terms of TA3, that's something that we're still looking at. And really the number of features is going to depend on where they're from and also the age of your individual. So if your individual is very young or very old, you generally need fewer features if they're the right features to capture that. In middle age, we really need more features throughout the entire body. So if you have, I think in my dissertation, I had estimates that were fairly accurate with about 15 features, but those were hand selected to cover as much of the age, to provide information throughout all of adulthood. Like, so the transitions were separated throughout the whole lifespan. If you have, let's say, 10 or 15 traits, but they're all concentrated in the upper limb or all in the thorax, chances are your results are going to be more biased, but we can't really say that for sure because we haven't run all of the simulations yet.
Yeah, I completely agree. This is a really interesting question, especially, in terms of real world application. A lot of the times you are getting fragments and a lot of unidentified human remain cases. You don't get, a lot of the skeletons. So
I would also say one thing I don't think I mentioned in the presentation is that when we selected the traits, not only were we trying to select the thresholds to be at different points in the age distribution, so they covered the whole thing, and so that we would get them throughout as much of the skeleton as possible, we were also picking things that could be identified in fragments. So one of the things I realized in this project, especially when I did my archaeological work, sorting through giant boxes of fragments, is that a lot of the traits preserve really well because they're in areas that tend to fragment off in small chunks, and they were chosen in a lot of cases for that. So if you are really good with your fragmentary osteology, or you get used to looking at the textures and the shapes in those areas, even if you only have like a handful or a box of tiny fragments, chances are you're still going to be able to observe a lot of these features.
All right. Well, I don't see any more questions in the Q&A pod. Are there any more? If anyone in the audience, feel free to just put any additional questions in the Q&A pod before we wrap up. All right, and we have a question from an undergrad. Are there any specific institutions or programs you recommend applying to if you want to pursue the same kind of work that you're doing?
Oh, that's also a tough question. I would just say really kind of think about which aspect of the work that you want to do. Do you really want to focus on a program that teaches you to be a really strong osteologist and look at human variation, and you're really interested in the bones? Are you interested in sort of the underlying population variation and the genetics? Do you want to look at the cultural and environmental factors that are influencing bone development and growth and the aging process in general? Or are you interested in the statistical models? And just realize that those are going to be very different programs. So when you're looking for people that are interested in age, consider which aspect they're interested in. And if you're looking at people that aren't necessarily interested in age, think about whether the methods or the techniques or the approaches that they're using in their questions could be translated to answer questions about age. Because I think the more cross-pollination and the new, more sort of out-of-the-box thinking that we can have, taking ideas from different fields and looking at aspects of this problem, the better off we're going to be.
No, that's great to know. Yeah. And I know you mentioned, the trait manual, it's available in PDF. I think someone's asking if you happen to have a fillable data collection form.
We do not at this time. We're waiting to update the form until we have a kind of final version of the traits, because not all of that data is going to be collected. I know Jacqueline created a fillable collection or fillable version of the form in Access, but again, because you can't translate those data into any sort of age estimation program at this point, we didn't think it would be that helpful, but I would be willing to ask her if she'd be willing to share it. If that's something people are interested in. But again, we'll be creating a new version of the form coming out in 6 months. So when that happens, we can create a fillable version for people.
Yeah, that's good to know. Yeah, if anything that in the future that becomes live, or if anyone else has any questions about it, surely reach out.
Yeah, the other thing that we realized when we were collecting our data, the reason that it's all in paper and that it's not a fillable PDF, or that we didn't enter it in electronically, is just because typically we were either wearing gloves or the collections were very dirty or very greasy. And so we did everything via paper. We also found that it was easier to check mistakes and to verify the data collection if we did everything via paper. It kind of slowed us down and forced us to look at the data manual while we were doing it. So that's just why everything's on paper at this point.
Great. All right, I think we don't have any more questions in the Q&A pod. Again, if anyone has any additional before we wrap up, but Dr. Getz, if you have any other final thoughts.
No, just thank you for having me. And again, I feel like I have more questions than answers at this point, but please feel free to contact me or check out my website for updates. As I get updates from the team, I'll also try to put them up there if it's kind of a one-stop shop for new information. And I'm also always happy to answer questions or meet with people if there's anything that maybe we could talk out that we didn't get to answer today. So thank you.
All right, if there's no further questions, we're going to go ahead and end today's webinar. Thank you so much, everyone, for attending. And thank you again, Dr. Getz, for being here today.
Thank you for attending today's webinar. As you depart, we kindly ask that you take a minute or two to complete our post-webinar survey. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our webinars and continue providing the best experience possible. Lastly, we encourage you to check out our social media profiles, including Twitter, LinkedIn, and Facebook. You can find those links on the webinar page. There are also links to the Just Science Podcast SoundCloud and a link to subscribe to the FTCOE newsletter. Like, follow, or subscribe to stay up to date with everything the FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.